Hello everyone, welcome to my lecture on statistics and epidemiology. We will start with types of bias. First, the confounding bias. This occurs when the researcher is not accounting another factor that can affect the results. In this case, there is the third variable associated with both the dependent variable and the independent variable. For example, if we said that an outcome which is lung cancer is associated with smoking, the confounding factor in this case can be the age, because age can affect the chance of cancer occurring among participants. So in this case, age is a confounding bias. Now the exclusion bias. Exclusion bias occurs when a group of population is excluded, then the result will not be applicable for this group. For example, if you do a research on certain population and you exclude the geriatrics, for example, the results of this study will not be applicable on geriatrics. The lead time bias. This occurs when a diagnostic test is used in one group is detecting the disease earlier. It seems that the patient is living longer. For example, if we are going to do screening for certain disease by two methodologies, one of these methods is more sensitive than the others, then patients are going to be detected earlier. And in this case, if we compare the two groups, we will find that it seems that these patients who are detected earlier are going to have longer life, and in this case, this is going to cause lead time bias. Recall bias. In prospective studies, when the patients are asked about an old event in the medical history, then the patients, for example, with cancer, can be more motivated than healthy individuals to recall their past episodes of chemical exposure. So the recall bias is very important in prospective studies in which we need the patient to remember a certain exposure. Also, we have the attrition error, which is a systemic error occurs when the participants are lost during the study. For example, we are comparing two groups, but parts of this participant are dead during the study. Then we cannot compare the two groups again because this is going to cause an attrition error. We should consider this error during such study. Interobserver error. This is difference in the interpretation between at least two individuals making observations of the same phenomena. That means if we have more than two researchers or observers and they had mistakes in their or difference in their interpretation of results, such as measurement errors, this can result in interobserver error. We can overcome such an error by decreasing the number of observers. Also, we have selection bias, in which we selected participants from different groups who are not sharing certain criteria. For example, in case control studies, the participants in the control group and in the cases group should be the same. And this is common among these types of studies. For example, if you involve one group who are inpatients and another group who are outpatients, so to avoid selection bias, we need to choose participants who are comparable or not different. The effect modification. This is occurring when direction or magnitude of the effect of independent variable on a dependent variable or outcome varies depending on the level of third variable or effect modifier. This is occurring when there is an effect modifier that is changing the outcome. Incidence and prevalence. Incidence only considering new cases of the disease, while prevalence is considering old and new cases. Incidence is the absolute risk. How we can calculate the prevalence? Here is an example. of a case, we are going to do calculation. In a survey of 1,150 women who gave birth in Spain in 1988, a total of 468 reported taking multivitamin at least 4 times a week during the month before becoming pregnant. Now we need to calculate the prevalence of frequent multivitamin use in this group. In this case, the numerator will be the 468 multivitamin users, and the denominator is the total number of women, which are 1,150. Now, how we are going to calculate the prevalence? We are going to divide the 468 over the 1,150, then we are going to multiply by 100 because prevalence is going to be calculated as a percentage. So here the answer is going to be 40.7%. Then the prevalence is about 40.7%. Now let's do the same for calculating the incidence rate. Here we have the diabetes follow-up study, including 218 diabetic women and 3,823 non-diabetic women. So we have two groups, diabetic group and non-diabetic group. By the end of the study, only 72 of the diabetic group and only 511 of the non-diabetic group had died. The diabetic women were observed for a total of 1,862 persons year. The non-diabetic women were observed for a total of 36,653. So the total number for each group is identified. Now calculate the incidence rate of death and for both groups, diabetic and non-diabetic women. Now how we are going to do this? First, for diabetic women, the numerator will be 72, while the denominator is going to be the total number of diabetic ladies. So the person time rate is equaling 72 divided by 1,862, and this is going to give us 0.0386 death per person per year. Then we need to do this, if we want to do this per 1,000 persons in a year, we are going to multiply it by 1,000. So it is going to be 38.6 deaths per 1,000 person per year. The same is going to be done for the non-diabetic woman. Here the numerator is the 511 and the denominator is the total number of non-diabetic studied population, which is 36,653. Here the person time rate is going to be 511 divided by 36,653, and this is going to give us 0.0139 death person per year. Again, we are going to multiply by 1,000 to have the incidence per 1,000 person. It is going to be 13.9 death per 1,000 person in a year. The relative risk or the risk ratio, this is providing the increase or decrease in the likelihood of an event based on some exposure. That means it is the ratio of the probability of an event occurring. For example, if we have two groups, one group exposed to certain drug while the other group not exposed to this drug, then we are going to assess the developing of the adverse drug resistance to a drug in these two groups. So the ratio of probability of occurring of the adverse drug reaction among the exposed group to the probability of occurring of this adverse drug reaction in the non-exposed group. The RR is derived from study designs where the study population is selected based on exposure. So here we have exposure. To measure the relative risk, we need a certain exposure. So it is commonly done in cohort studies and case control study design. and may have different names depend on the context. So we can find different nomenclature for the relative risk according on the context. In cohort mortality study, we call the relative risk standardized mortality ratio. So if you are asked to calculate the standardized mortality ratio, then you should understand that this is the relative risk in a cohort study. In cohort incidence study, the relative risk is having another name, which is standardized incidence ratio. So if you are asked to calculate the standardized incidence ratio, you should understand that this is the relative risk. Also in morbidity cohort or the cross-sectional studies, it is called the prevalence ratio. So if you are asked to calculate prevalence ratio, you should understand that this is the relative risk. In order to calculate the relative risk, we are going to check this example. The probability of developing allergy among users of perfume was 20%, and among those who are not using the perfume is 1%. We need here in this case to calculate the relative risk of allergy associated with users of perfume. So we have an exposure, which is a perfume, and the outcome is allergy in one group and non-allergy in other group. So here we are going to calculate the absolute risk among the group of exposure divided by the incidence of unexposed group, or the absolute risk among non-exposed group. In this case, to calculate the exposure or the absolute risk, we are going to divide those who are exposed to the perfume with presence of allergy divided by the total group, which is in which there is allergy, and those who are having no allergy. So it is going to be 20/100. In the other case here, in non-exposed group, the absolute risk is going to be the allergy occurrence in non-exposed group divided by the total group who are having allergy and who are not having allergy. So it is going to be 1 divided by 100. So the answer is going to be 20 for the relative risk. This is how we calculate the relative risk. We are going to divide the absolute risk in the exposed group by the absolute risk in the non-exposed group. Now, how we are going to interpret this relative risk result? For example, in our result, it was 20. So it is considered more than 1. That means the exposure to perfume is a risk factor for getting allergy. But if we have an answer which is equaling to 1, that means there is no association between the exposure to perfume and allergy. If we had the relative risk less than 1, if the answer we got it was less than 1, that means the exposure to perfume is a protective factor against allergy. So treatment, for example, is negatively associated with an outcome. And a relative risk of 2 means that the rate in the exposed group is twice at risk than the non-exposed group. When the rate of exposed group is equaling to the rate in the comparison group or equaling to 1, that means there is no association between the exposure and the disease. Now we have another important assessment tool, which is the attributable risk. By attributable risk, we mean the difference in rate of condition between exposed population and unexposed population. Mostly it is calculated in cohort studies where the individuals are assembled on exposure status and followed over a period of time. The investigators are counting the occurrence of the disease. In the cohort study, then we are going to subdivide the level of exposure and the frequency of the disease compared between these groups. To make this more clear, the attributable risk is having another name, which is risk difference or rate difference. So from this name, you can understand more better that it is the risk difference or the rate difference. Now, how we are going to calculate the attributable risk? In this example, amoxicillin and ampicillin are used for treatment of the same infection. We found that amoxicillin 90% is successful in treating this type of infection, while ampicillin was successful in 65%. So if we want to measure the rate difference, we are going to minus the risk in those exposed minus the risk in non-exposed. So it is going to be 90% minus 65%, which is equaling 25%. So here, the one is considered exposed and the another is considered unexposed. If we want to measure the rate difference between the amoxicillin and ampicillin, it is going to be 25%. This R is the absolute risk or incidence. So the affected group divided by the total group who are affected and non-affected. So the absolute risk reduction is equaling to the incidence in the control group minus the incidence in the treatment group. Let's understand what is the number needed to treat. The number of patients who need to be treated in order to prevent one additional bad outcome is an important in assessment of the usefulness of treatment prophylaxis. So here the number needed to treat, it is going to be abbreviated as NNT, is equaling to 1 divided by absolute risk reduction. So if we want to calculate it, we are going to divide 1 over absolute risk reduction, which we already calculated in the previous example. The absolute risk reduction is equaling incidence of events in the control group minus incidence in the treatment group. Another method of assessment is the odds ratio. And the odds ratio is the measurement of association between the exposure and the outcome. So here we are measuring what? An association. The odds ratio, because it is ratio, we are going to divide the odds of exposure in cases divided by the odds of exposure in control. How we are going to do this? For example, we have two groups with the disease and non-diseased. The first group exposed to treatment who got the disease are considered as A. Those who didn't get the disease, although exposed to the treatment, are going to be B. The non-exposed control group are going to be C with the disease, but without disease, they are going to be considered as D. Here, the odd ratio is going to equal A, which is the exposed group with the disease. That means they are getting the disease after exposure to the treatment. They are divided by C, which is those who are diseased without exposing to the treatment. So these are deceased. Both are deceased. One group is getting the treatment and another group not getting the treatment. Okay? This is going to be divided by B and D, B over D. What is B? B, this is the group who exposed to the treatment and not get the disease. And D, these are the group who is not getting the disease, although they are exposed to the treatment. So these are non-diseased. So we are going to divide the deceased over the non-deceased. Okay? Deceased with exposure over deceased without exposure, divided by non-deceased with the exposure, divided by non-deceased without exposure. So if we want to calculate in this example the odd ratio in the cases, here these are exposed group who eat fish and get sickness, and this group is not exposed to the fish but they get also the sickness. We want to calculate. We are going to take for first the diseased group, exposed and non-exposed. So we are going to divide the 5 by the 2. Okay, it is going to give us 2.5. Now we are going for the control group who are not diseased. We are going to get to take those with exposure divided by those who are not exposed. This is going to give us 0.3. Then we are going to divide this 2.5 over the 0.03 and the result is going to be 8.33. This is how we calculate the odd ratio. In this example we had the result is 8.3. If that means it is more than 1. This is suggesting that the odds of exposure are positively associated with the adverse outcome. So eating fish is positively associated with the illness. Here the expression of the odd ratio result is going to be either positive association or negative association, because we said it is already done for measurement of association. The main purpose of the odd ratio is the association. This is why we are expressing it as positively associated and negatively associated or no association. So if the result is more than 1, then there is positive association between the disease, the exposure and the outcome. But if it is less than 1, then the odds of exposure are negatively associated with the adverse outcome. So there is no association between the exposure and the result. In case of 1, that means it is equal to 1. This suggests there is no difference between the two groups. There is no association depending on the exposure. Now let's shift to another important topic, which is study designs. In this hierarchy, you can see that on the top of the hierarchy, we can find the meta-analysis, which is considered the best design of studies, while the base of the hierarchy or the pyramid is showing the case control, the opinion papers and letters. In the middle, we have the randomized control trials, followed by the cohort studies, case control studies, cross-sectional studies, animal trials, in vitro and the studies, and finally, as we said, the case reports, opinion papers. This is showing the arrangement of the designs depending on strength. So the top of the pyramid is the most strongest scientific evidence design of a study. So the meta-analysis is to make use of data from prior studies to synthesize new data, determining more precise statistical information for certain research question. So the most important thing in the meta-analysis here that we are going to use data from previous studies and reuse it and do again analytical study. So we are going to analyze the data from previous studies. The second study design is the randomized control trials. And here there is random different intervention to subject testing efficacy or effectiveness. So we are going to test for efficacy or effectiveness of what? Of healthcare services, healthcare technologies, and there are two phases in these control trials. The first phase is the stage at which the patient is going to receive a new drug under the study. The second phase is when the patient is a control and receive nothing or receive placebo. In the two phases, they should be separated by a wash period. This is very important to have a wash period to avoid the carryover effect of the drug used in the first phase into the second phase. So to avoid the mix-up or the carryover effects, we are going to have washout period. The third type of designs is the cohort study, in which two or more groups of individuals are having similar characteristics who are differing on the basis of exposure. So the only difference between the two groups or the individuals are the exposure to a particular agent. This is followed over certain time. So in cohort study, we are following the patients for certain exposure. Why? To determine how many individuals in each group are going to develop the particular disease. So the cohort studies is mainly based on exposure and follow-up of cases to determine the development of the disease. The fourth group is the case control study, and this is showing the association but not causality. If we want to check for the causality, we are going to do what? Cohort study. But if we want to check for the association, we are going to do case control study. In this case of case control study, we are going to assess the exposure of interest among diseased group and non-diseased group. So we have two groups, one with the disease and one without the disease. And here we are going to check for the association. And if we want to check for association, we are going to do what, or calculate what? The odd ratio. And this is ideal in cases of outbreaks. In cases of outbreaks, we need to know the association between certain factors and the disease. One potentially problematic factor here is the selection bias, because we need to know that the group of study and the control group should be the same or should be similar, so to avoid what? To avoid the selection bias. Another group is the cross-sectional study, and this is very important to show the disease and exposure. Here we are mainly concerning with the risk factors. So this is also important because the data collected at a given time point, but refer to past medical history and showing a possible association and use for the prevalence assessment. If we are concerning with the past medical history, in this case, we are at risk to have recall bias. So the recall bias is one of the important problems associated with cross-sectional study. So one of the limitations of the cross-sectional study is the recall bias. This type of studies, cross-sectional studies, is mainly for prevalence assessment. We are here considering prevalence assessment. And the data is collected, as we say, in a given point time. Also, we have the retrospective cohort study, and this type of study are conceived after some people have already developed the outcome. So here, for example, we are going to look in patients who are having diabetes. Then we are going to jump back in order to identify a cohort of individual at point of time before they have developed the outcome of interest to establish a case exposure. We are going to look in the records in order to identify a factor that resulted in this outcome. For example, obesity. We are going to look for patients who are already having diabetes type 2. Then we are going to look in the records for the factors related to obesity that showing that this diabetes is due to obesity. The opposite is occurring in prospective cohort study. In prospective cohort study, we are going to follow up patients who are obese for the development of diabetes. The predictive value, or the likelihood that is a positive result is true positive, means that the probability of the disease to be in the patient who is having positive result is true. So the positive predictive value is equaling the true positive divided by the total positive, true positive and false positive. This is the number of confirmed positive by confirmatory test divided by the total true positive who were confirmed by screening test. So if we are screening for example, HIV by ELISA, and we have 30 positive cases, then we are going to have also a confirmatory test, which is Western blot. If the Western blot, for example, result was showing 15 positive cases, then the other 15 who were positive in the ELISA are considered false positive. If we want to calculate the total positive, then we are going to add the truly positive by the Western blot and the falsely positive by the ELISA. So this is considered the total true positive. If we want to calculate the predictive value or the likelihood, we are going to divide the true positive measured by the confirmatory test, which is Western blot 15. It is going to be divided by the 30 cases who were truly positive and falsely positive. The accuracy is defined by how well a calculated value representing the true or actual value. The low accuracy is corresponding with high systemic error in the measurement. So accuracy, when it is low accuracy, then there is systemic error. While the precision is how reliable a calculated value can be replicated. So if we can have the same result after repeating the test, then we are having a precise test. The low precision is correspond with the high random error in the measurement. So it is associated with random errors. The precision associated with random errors, while the accuracy is associated with systemic errors. Also, the precision is meaning the positive predictive value. So if we have a positive predictive value, the more positive predictive value we have, the more precise test we are having. This is expressing the precision of the test. Here in test number 1, we have a result which is very similar or very similar to the test number 2, and there is no big difference from the test number 3. So this test is considered precise. While here in accuracy, we are not comparing the same method, we are comparing different methods. Here we are comparing different results, but in the accuracy we are comparing methods. For example, if we are measuring the HIV by ELISA, and if we are measuring the HIV by Western blot, we want to check for the accuracy of the ELISA in comparison with the Western blot. Here, if the method 2 give us a reading of 501 and method 2 give us 502, while the method 3 give us 500, all the results are very near to each other. This is showing that the 3 methods are accurate, or the one we want to compare is accurate in comparison with the other methods. Whenever we want to select a test, we are going to check for the test sensitivity and specificity. For example, for screening purposes, we are going to look for sensitive tests more than specific tests. But for confirmatory tests, we are going to check for more specific tests. But in the screening process, if we want to raise the threshold, or if we want to increase the threshold of a screening test, then we are going to decrease the sensitivity. The sensitivity is showing us few false negative, and in this case, few cases are missed. The more cases you want to detect, the more sensitive test you are going to pick. Now, how we are going to calculate the sensitivity? Sensitivity is calculated by dividing the true positive on the divided by the total disease. Here you can see the total positive divided by the total disease. Total disease means the true positive and the false negative. All of them are disease. So we are going to divide the true positive by the total diseased. For specificity, it is showing us few false positive. And when we want to calculate it, we are going to check for the total negative, the true negative, and we are going to divide it by those who are healthy. Healthy, that means they are having false positive plus true negative. All these are considered healthy. And all these are considered diseased. Now we are going to go for another topic, which is prevention strategies. Here we have different definitions, like primary prevention, which is a strategy put in place before the disease occurs. Here, the most important point that this strategy is before the occurrence of the disease. Here, example for these strategies of primary prevention is the immunization and cessation of smoking program. So here we are preventing the disease from occurrence. The next level is the secondary prevention, in which it is involving establishing screening methods to detect disease at early stage. Here the purpose of the secondary prevention is screening. We want to detect the disease as early as much as possible. The third level is the tertiary prevention. In the tertiary prevention, we are going to treating an existing disease in order to prevent the complications. So here in the tertiary prevention, we are trying to stop the complications from occurring. Another type of prevention is the passive prevention. In the passive prevention, the strategies are measures put in place to protect the person with their active efforts. For example, airbags in cars and seat belt. The passive prevention here, the protection for the person is by the person without their active effort. So this is why it is passive, because there is no active effort. For example, we are going to prevent the trauma by applying the airbags and by putting the car seat belt. That is all for today. I hope you enjoyed the video. If you like the video, please subscribe to my channel to receive the new videos. Thank you very much.